Hello there, folks. Today is April 17. It is, I've had some problems this morning with doing the lecture and recording it and all of that. I'm finally able to stream it to you all at 9 a.m. here. So I apologize for all of the confusion. Some of that was my fault. Some of that seems like it's Twitch's fault. Either way, we're going to make do. Like we've been doing. So I do want to talk today about power series, but before I get to that, I want to say something about the slip that I solved for, or that I assigned to you yesterday as part of yesterday's lecture. So in that problem, I was asking you to test this series here for convergence, yes? And as many of you gathered from the context of that lecture, what I was expecting you to do was to use the ratio test. I know what I'm talking about vaguely, okay? The ratio test. So if you use the ratio test, you're going to be looking at the limit as n approaches infinity of a sub n plus 1 over a sub n, all right? And that's equal to this amalgam here. So let's just walk through. A sub n plus 1, what that is what you obtain by replacing the n here by n plus 1. Okay? But you also do it for the n down there. So every n that I see, I'm going to replace by n plus 1. And if I do that, I get this expression, n plus 1 squared over 2n plus 1 factorial. Okay? So that's a sub n plus 1. Then I'm going to multiply that by the reciprocal of a sub n, because I'm dividing by a sub n. And a sub n is just written in front of my face. There it is. So there it is. The reciprocal. Okay? Then I do some algebra. And I think it's convenient very often when using a ratio test to group together like terms or common, sort of superficially resembling, terms which superficially resemble one another. So this n plus 1 squared kind of looks like this n squared, so I'm going to sort of group them together in a single fraction. And the factorials kind of look similar, so I'm going to group those together in a single fraction. Please note that 2n plus 1, okay, is equal to 2n plus 3 factorial. Now, for some reason, a lot of people thought that it was 2n plus 2 factorial, but that's just a matter of thinking that you're adding 1 to this 2n plus 1, which you're not doing. You're replacing the n by n plus 1, which is this expression, and if you expand out this expression and evaluate it, you get 2n plus 3 factorial. Okie doke. And then, thinking about this limit right here, I hope that you're at the point in your life where you can say more or less immediately that that limit is 1, but if you want a justification, what I would do is to factor out from the n plus 1 an n. Okay? If you factor out from the n plus 1 inside the square, an n, you get n times 1 plus 1 over n, and then you can, because exponents distribute over products, this is the same as n squared times 1 plus 1 over n squared. And so the n squared upstairs and the n squared downstairs kill each other. We have a 1 over n, which as n goes to infinity dies, and so what we are left with in this limit is 1. What about, though, the limit of the other side, of 2n plus 1 factorial over 2n plus 3 factorial? What do we do with that now? Well, 2n plus 1 factorial is this product here. And 2n plus 3 factorial is this product down there. And so what we can do is just cancel all these terms, massive die-off in factors, okay? Until what we're left with, the only things which survive all of this carnage is 2n plus 3 in the denominator and 2n plus 2 in the denominator. So we're left with this expression. If that's not clear, you should ask, okay? Now, as n goes to infinity, this thing here goes to 0, right? That's the limit as n approaches infinity. This is equal to 0. So in particular, the fact that this goes to 1 doesn't matter because this thing is going to 0. So the entire thing is going to 0. And 0 is less than 1. And by the ratio test, that implies that the series converges. Okay? So I hope that that is more or less clear. Today what I want to talk about is more on power series. All right. And here is what I want to say. I'm still live. I just want to make sure everything is fine. Yeah, looks okay. So power series. And today is April 17, just to keep things current. All right, and dated. All right, so here, yesterday I introduced the notion of power series, did I not? But today I want to say something, or give a notion of power series which is slightly more general. Here's what I want to say. Definition. Power series. Centered now at x equal to c. So this is the notion that I'm defining. And I'm tagging this new phrase, a power series centered at x equal to c, is a series of the form sum from n equals 0 to infinity of a sub n times x minus c to the nth power. Okay? So the difference between what I'm writing here and what I wrote yesterday is that yesterday I only talked about power series which were centered at c equal to 0. All right. Now, what is this? What is this? What is this crazy thing here? So let's forget about this equal sign. Look at this thing. What is it? The way that I'd like you to think about this is important, is I'd like you to think of this as a function. Okay? This is a function which eats x. The input is still x, just like all of our other functions, like sine of x or e to the x. The input there is x. The input here is x. So what that means is you can replace x by certain values. Certain values. Why do I say it like that? Why not all values? Well, because we know functions have a domain, right? Like, for example, 1 over x, you're not allowed to stick whatever you want into 1 over x, because if x is 0, then you get something which is undefined, and that's bad. So we have a notion of domain of functions. What is the domain of the function I've got written here? Well, we'll come to find out that that's going to be called the interval of convergence. But let's not go there yet, okay? But the main point I want you to have right now in your mind is that this is a function. So this is the sum from n equals 0 to infinity of a sub n times x minus c to the nth power. If I write out the first few terms, what that looks like is starting with a equal to 0, or n equal to 0, we get a sub 0. Sometimes people say a naught. I think that's a British thing, but it carries over into the United States for some reason. A naught plus a1 times x minus c to the first power. Oh, by the way, in the context of power series, in the context of calculus, anything to the 0th power is 1, okay? Anything to the 0th power is 1, all right? So, yeah, whatever. Cool. Plus a sub 2 times x minus c squared, that's the next term, and dot, 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 all right? These numbers, these a's, are called coefficients of the power series. Coefficients of the power series. All right. And they're just numbers. They don't depend on x. All right. So that's the notion. Here are some examples. The simplest non-trivial example I can think of probably is this one. This here is a power series. It's centered at c. A sub n here is equal to 1 for all n. Okay, those are the coefficients, the sequence of coefficients of this power series. A sub n is 1. And you can see that because, well, it's just there. And what's c? C is 0. The center of this power series is 0. I mean, we could change that up a little bit, right? We could make the center of this thing be some other number. Like, what if we made this be x minus 2 to the n? Well, then the a sub n would not change. It's still the same. It's still 1. But now c is equal to positive 2. We could change things up more. What if we had, for example, sum from n equals I don't know why I started this at 1, can start at 0, of x plus 5 to the nth power divided by 2 to the n times n factorial. Well, for this series here, what's playing the role of a sub n is 1 over 2 to the n times n factorial, and what's playing the role of c is negative 5, right? Because we subtract from xc. So if I have x plus 5 here to the nth, I have this. Okie doke. Maybe one more example, just as a bit of a challenge to you. What if we were to think about the sum from n equals 0 to infinity? Oh, wow. You know what? I don't even want to say that out loud. Okay, we're not going to go there. All right, these are some good examples here. All right. Now, what I want to do is shove down your throat some facts. Okay, these are really interesting facts, but I'm not going to justify them or prove them in any way. Okay. So some definitions first, maybe. So the set of values of x which make a power series converge is called the interval of convergence. Which we will initialize IOC for the sake of brevity. Okay? Now, as the name suggests, the fact is the IOC is an interval. But I want to say a little bit more about the interval. I want to say it like this. It's an almost symmetric interval centered at x equal to c. So what the hell am I talking about? So if I draw a real number line here, here's a real number line, all right? Here is x equal to c on that real number line. Then what I'm saying when I say almost symmetric, well, first of all, let's forget about the word almost for a second. Let's think about the word symmetric. What do I mean by a symmetric interval centered at c? What I mean is it's an interval for which this distance right here is the same as that distance right there. So in locating with the endpoints, we might call this endpoint here c plus some number r. And if the distance between c and c plus r is supposed to be r, and if this thing is supposed to be symmetric, then this distance is supposed to be r. So we can call this point on the real number line c minus r. Okay? The fact is, the power series is absolutely convergent on the interior of the IOC. Okay? It is divergent outside the IOC. So these two things give very definitive statements about where this thing converges. It converges on the interior for sure, and it diverges outside of the interval of convergence. So we have, in fact, we have absolute convergence on the interior here. And outside here we have divergence. The only thing that's a little unclear by these two statements is what's going on at the endpoints. At the endpoints, anything can happen. Literally anything can happen. And that's what I sort of mean by this almost symmetric business. Because you can have, for example, a situation in which you have convergence here, absolute conditional convergence, whatever, here, but straight up divergence at the other endpoint. So it's not symmetric, right? Because if we have convergence here and divergence there, that's not symmetry, right? But we have almost symmetry, right? You could have divergence at both. You could have convergence at both. You could have absolute convergence at one, conditional convergence at the other. All of these things can happen, okay? So for that reason, we say that this thing is almost symmetric. By the way, this number r, which is sort of the half width of this interval of convergence, r is called the radius of convergence. All right. Sorry. Okay, cool. Now, listen, please. If you don't understand some of these facts, I would like you to pause the video, rewind the video, and then try to listen through these facts again. Because I really want you to take this on board and have a mental model or something set up inside of your head to think about this. It's very important, all right? What is it? What am I saying? I'm saying that the set of values for which a power series like this one right here, a general power series, the set of values which make this power series converge looks like an almost symmetric interval. The half width of that interval we call the radius of convergence. Okay, it's a number r. Outside of the interval of convergence, we are guaranteed to have divergence. Okay, and on the interior of the interval of convergence, we have absolute convergence, right? The slightly stronger form of convergence. All right. So that is, well, what I want to say about that. Now let's actually get to computing some interval of convergences, shall we? All right. Now, I'm just going to state this again as another fact, because I want to give you a tool which is very expedient for computing the interval of convergence, because we care about that question of what the interval of convergence is. All right. I'm going to give you a tool, but before I introduce that tool, all right, I'm going to do an example. So here's an example. And I hope that this works out okay. Let's see. So yeah, let's find the IOC, interval of convergence, of the power series, sum from n equals 0 to infinity of, let's do 3x to the nth power. Now I claim that's a power series. Now it might not be written precisely in this form, but we can make it so. How? Because this is exactly the same, just by rules of exponents, as 3 to the n times x to the n. I hope we can all agree with that. Yeah? Okay. Now, one thing that I want to say is we actually know what the interval of convergence of this thing is without doing any work at all. Remember what the interval of convergence is. It's the set of values of x which make this series converge. And I claim, and I'm right, that we know already, given the technology that we've already developed, what values of x makes this thing converge. You know why? Because in this very special case, this here is a geometric series. This is very special. Okay, this is not going to happen all the time by any means. But this is a geometric series. And let's think about then what A is and what R is. Remember, those are the parameters that you're allowed to tweak in the geometric definition of a geometric series. So A is always the first term. The first term here is what we get when we stick n equals 0 in, and that's 1. Can we all agree? Now what's r? R is the thing that we multiply the previous term by to get the next term. And I hope that it's clear that here r is 3x. Right? I mean, we can write out this series, right? What is it? It's 1 plus, now if I stick in n equal to 1, I get 3x. What's my next term? It's going to be 3 squared, which is 9 times x squared. Next term is going to be 27x cubed, etc. So to get the next term from the previous, you multiply by 3x. So it's geometric. And so what that means, this implies that we get convergence. Remember when a convergence happens, exactly when the condition for a geometric series to converge is that, remember, the absolute value of r is less than 1. But what's r? It's 3x, right? But when is the absolute value of 3x less than 1? How can that happen? Well, if the absolute value of something is less than 1, then what that means is that that something must be between -1 and 1. But when does that happen? We can, or for what values of x does that happen? That happens by dividing by 3. We can learn that this happens when x is between -1/3 and 1/3. Okay? So I think I know what the interval of convergence is for this series. It's when x is between -1/3 and 1/3. And that's all fine and good. That's all dandy. That's great that we have this way of figuring it out. But what I want to do for you right now is to show you a method that will always work, okay, and is very handy for doing more complicated problems, for which more complicated power series which are not geometric. So I'm going to state this as a fact, and then we're going to apply this fact to this series to see that it really works out. Fact. Is this the way I want to do it? I think so. So, given a power series sum from n equals 0 to infinity of a sub n times x minus c to the nth power, okay, we can compute the radius of convergence, r, the ROC, the radius of convergence, by the following fact, or the following calculation. The limit as n goes to infinity of the absolute value of a sub n plus 1 over the absolute value of n, of a sub n, rather. And it turns out that this is equal to 1 over big R. Okay? Now, this is a little bit of a this is a little bit strange, because sometimes you're going to find that this quantity right here is 0 or infinity, and then how do you interpret 1 over r being equal to either 0 or infinity? So let me say, if the limit is 0, okay, so if this side here is 0, then 1 over r, you think of, so if you want to set 0 equal to 1 over r, in principle, what that means is, you know, r is not, there's no solution. There's no solution to the equation 0 is equal to 1 over r. But what we're going to interpret that as meaning is that r is equal to infinity. This kind of makes sense intuitively. 1 over infinity is like 0, right? So we're just gonna stipulate this. And similarly, if the limit is infinity, so if this side here is infinity, what we're going to do is interpret the radius of convergence as being 0. Okay. So this is a very useful fact, which I'm just shoving down your throat, which I could justify through a ratio test argument. Through a ratio test argument, I can justify this. And maybe if I have time later, I will put up a bonus video sort of explaining why this is so, because this is definitely accessible to you, given what you understand about the ratio test. But for now, in the interest of time, I'm just going to run with this fact here, okay? And we're going to apply it to this series now. So, example, or continued, let me say it like this. We're going to apply this, this machine right here to this guy here. So in thinking about this series, remember, we rewrote this series as the sum from n equals 0 to infinity of 3 to the n times x to the n. So you got to think, what's playing the role of a sub n here? Look at this fact. We want to know what a sub n is. So what's playing the role of a sub n here is 3 to the n. And what's playing the role of c here is 0. It's centered at 0, and the coefficients are 3 to the n. So what we're going to do is we're going to look at the limit as n approaches infinity of the absolute value of 3 to the n plus 1 divided by the absolute value of 3 to the n. Now, of course, the absolute value of 3 to the n plus 1 is just itself, because 3 to the n plus 1 is always positive. Similarly for 3 to the n. And so what this means is that if we divide, we get the limit as n approaches infinity of 3. Which is equal to 3, because it doesn't depend on n. Okay? So then what this suggests is that r, which is supposed to be 1 over r here, right, as per this fact, that means that r is equal to 1/3. I hope that's clear. That's the radius of convergence. So what that means, let's recall the set of facts. And again, this is where I want you to have the mental model here. This picture is very valuable to have in your head. For this series here, centered at c equal to 0 in this case, we know that we're going to have a convergence between 0 minus 1/3, 0 minus 1/3, and 0 plus 1/3. So what we're going to have is the following picture, at least thus far. Here's 0, here's negative 1/3, and here's positive 1/3. So we're going to have absolute convergence inside here. We're going to have divergence out here and divergence out here. And we are, in what's mysterious is what's going on at these two endpoints. That's a mystery. We don't know, in principle, what's going on at those two endpoints. So what we do to figure out what's going on at those two endpoints is we manually check. What do I mean by that? Manually check endpoints. What do I mean by that? I mean that we take these values, x equal to negative 1/3 and x equal to 1/3, and we just shove them into this expression. So I'm going to continue that on another sheet of paper. I'm really burning through paper like crazy today. So at x, so reminder, yeah, example continued. So at x equal to negative 1/3, what does the series look like? So the series, remember, was this one. So if x is negative 1/3, then just plugging that into here, we get the sum of 3 to the n times negative 1/3 to the nth power. But what is that? That's the sum of 3 to the n times negative 1 to the n over 3 to the n. That's just rules of exponents. These 3 to the n's die, and what we're left with is the sum from the sum of negative 1 to the n. These are all from n equals 0 to infinity. And what do we know about this series? It's divergent. That's what we know. Why do we know it? We know it because of the divergence test. You remember the divergence test? The divergence test says that if the limit of the sequence of terms of a series is anything other than 0, then the series diverges. So think about what the sequence of terms here is. It's negative 1 to the nth power. What does that sequence look like? It looks like 1, negative 1, 1, negative 1, 1, negative 1. In other words, it never settles on any particular value. The limit does not exist. And so this thing is divergent. And so what's going on? So that answers what's happening at x equal to negative 1/3. How about x equal to positive 1/3? Well, that's just the sum from n equals 0 to infinity of 3 to the n times 1/3 to the n. And I hope you all realize that this is the sum from n equals 0 to infinity of 1. And now the divergence test is even more stark. This thing diverges. Because the limit as n approaches infinity of 1 is 1, which is not 0. So this is a divergent series. It blows up to infinity. Makes sense, right? You're adding up infinitely many 1s. Of course that's going to blow up to infinity. Okay, so in the end, what do we learn about the interval of convergence for this particular series, this one here? We learn that the interval of convergence is soft bracket, negative 1/3, comma 1/3, soft bracket. Which is, oh, by the way, which is exactly what the geometric series factoid told us. Okay? All right. Let's, of course, do another example, shall we? Sure. Let's do this one. Let's find IOC for the following guy. We have the sum from n equals 1 to infinity. And let's go ahead and do yeah. And this, no, we're going to start it at 1. Sorry, we're going to start it at 1 here. Let's do negative 2x minus 4 to the nth power divided by n. Yeah, let's do this. I like it. All right. Well, so I claim, first of all, that this is a power series. Now, if you look at the definition of power series, crud. Yeah, I think this is the sheet. Yeah, power series. Here is the definition of power series, right here. Okay. Now compare this with that. It looks different. How does it look different? It looks different because here I have a negative 2 multiplying by x. I don't have any coefficient or number in front of the x here. Okay? So I really need to fix that. I need to bring this expression into compliance with this definition. And I need to do that because I want to know badly what a sub n is so that I may apply my handy dandy fact, which we talked about here, for computing the radius of convergence. I need to know what the a sub n is. And notice that here, in the fact, we need to know what a sub n is, where a sub n is the same a sub n as the one in the definition. You with me? This is not in that form. But we can get it there. Here, watch. What I can do is factor out the -2, which is bugging the crap out of me, right? This is the same as -2 times x plus 2 to the nth power. Are we all comfortable with that? And this is equal to the sum from n equals 1 to infinity of -2 to the nth power times x plus 2 to the nth power over n. Now, I claim we are now in compliance. This is now clearly a power series, okay? And it's in compliance with what we've got here in the fact. What's playing the role of a sub n here? So a sub n is equal to all this garbage right here. It's -2 to the nth power over n. And what's playing the role of c here? Well, it's -2. Don't forget about the value of c there. Okay? Cool. So now what we're going to do is use this fact right here. All right. We are going to now compute the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by the absolute value of a sub n. Okay. And so what is this? So let's see, we're going to be looking at the limit as n approaches infinity. So the absolute value of a sub n plus 1, so we plug n plus 1 in for n here and there. We're going to be taking the absolute value of the whole thing. So we get -2 to the n plus 1 power divided by n plus 1. That's the absolute value of a sub n plus 1. And then we're going to be dividing by the absolute value of a sub n. But dividing by the absolute value of a sub n is the same as multiplying by the reciprocal of the absolute value of a sub n. And that's going to be n over -2 to the nth power with reciprocal. Now you should know some facts about the absolute value. Okay, so they're very good to know. So the absolute value of a product, okay, is the product of absolute values. You should know that. What? That fact. In other words, absolute values behave nice when it comes to products. They also behave nice when it comes to division. And they also play nice when it comes to powers. These are all true facts which you should sort of take on board and are useful to know. Okay. So now look at over here. If we think about applying these sorts of rules, then this is the same thing as the absolute value of -2 to the n plus 1 divided by the absolute value of n plus 1 times the absolute value of n divided by the absolute value of -2 to the n. Now, what is something like the absolute value of -2 to the n plus 1? What does that equal to? Well, maybe I'll even do it. As per this rule down here, this last one, as per that rule, this is equal to the absolute value of -2 to the n plus 1 power. Hey, what's the absolute value of n plus 1? Well, as n goes to infinity, n plus 1 is always going to be positive, right? So that's just n plus 1. What's the absolute value of n? Again, it's just n. We can drop the absolute value bar. Sweet. And what about here? Well, that's the absolute value of -2 to the nth power, again using this rule. Hey, what's the absolute value of -2? It's 2, isn't it? So this is the same as 2 to the n plus 1. And what's the absolute value of -2? Oh yeah, it's 2. So that guy there, I'm going to put underneath here, 2 to the n. And then what we're left with is n over n plus 1. We clear? Now, what is this equal to? So I'm not going to go through this. I'm not going to argue this, but you should know this piece here, as n gets larger and larger, goes to 1. You should be able to verify that in all sorts of different ways. We've done it so many times now. And of course, this piece here, when you cancel the 2 to the n upstairs and downstairs, you're left with just 2. So this piece here is obviously going to 2. This piece here is going to 1, so this limit is equal to 2. And I guess that 2 is equal to 1 over r as per this fact, where what big R is the radius of convergence. So this implies r is equal to 1/2. Okay? So our center is -2. If I add 1/2 to that, I get to -3/2, right? And if I subtract 1/2 from that, I get to -5/2. I hope I did that right. Arithmetic is hard for me. Yeah, I think that's right. And then what we have is absolute convergence here in the interior of this interval. But we have divergence outside. And you know what? We have a mystery at the endpoints. I've got 8 minutes, okay? So what we're going to do is keep continuing this problem on a new sheet of paper. So we're going to manually check why is the world so crazy? We're going to manually check endpoints. I don't know if you know this, but like when I was a kid, when I was your age, when I was from ages 0 to feels like 35 maybe 9/11 was pretty crazy, but things were not like this. They just weren't. Manually check endpoints. So what we're going to do is plug in these endpoints, x equal to -3/2 and x equal to -5/2. Let's see, which one do I want to do first? Sure. Let's do x equal to -3/2 first. Manually. So if I plug in x equal to -3/2 into my original power series, here is the original power series. Let me just rewrite it on this sheet of paper so I don't have to keep referring to it. So we have the sum from n equals 1 to infinity of -2 to the n over times x plus 2 to the n over n. Now if I plug in x equal to -3/2, -3/2 plus 2 is -1/2. This series becomes the sum from n equals 1 to infinity of -2 to the n times -1/2 to the n over n. I hope you can all believe that. Oh, no, I messed up. I'm sorry. I messed up. I'm sorry. -3/2 plus 2 is +1/2. My bad. +1/2. It's just 1/2 to the n. Okay? Now, can we simplify this? We sure can. This is the sum from n equals 1 to infinity of -1 to the n times 2 to the n, right? Times 1 over 2 to the n. So what did I do? -2 to the n is the same as -1 to the n times 2 to the n. So this became these two guys. And 1/2 to the n is just 1 to the n, which is 1, over 2 to the n, which is 2 to the n. But now, what's the sweet-ass thing that happens here? These guys die. And what we are left with is the sum from n equals 1 to infinity of -1 to the n's power over n. And I hope that you recognize that, because this thing is the alternating harmonic series. And why is the alternating harmonic series notable? Because it is the most famous example of a conditionally convergent series. And in particular, I'll just say it, it's conditionally convergent. Okay? So now x equal to -3/2 is no longer a mystery. We know what the behavior of the power series is there. It is convergent. What about at x equal to -5/2, the other endpoint? I'm doing this right? I think so, yeah. Negative 5 halves. So what that is, if we stick that in, we get the sum from n equals 1 to infinity of negative 2 to the n still. And now we have, when I plug in negative 5 halves here, we get negative 1 half to the nth power. Oh, you can't see any of that. Sorry. There. Okay? And now we can manipulate this. Oh, I'm sorry, all over n. We can manipulate the numerator here. This is the same thing. Well, let's see. We can rewrite it as negative 2 to the n. And I can think of negative 1 half as being 1 over negative 2, right? So this is 1 over negative 2 to the n, right? Just by rules of exponents. So those things kill each other. Interesting. So what do we get? Holy crow. We get the harmonic series. And what do we know about the harmonic series? It diverges. Okay. So, interestingly, if we go back to our picture here, we have divergence here. What? No, we have convergence here, conditional convergence here, and we have divergence here. So the IOC, the interval of convergence here, okay, it it excludes negative 5 halves, okay, but it includes negative 3 halves. That's the interval of convergence. I want to do one last example, which involves these weird edge cases in this fact, where what we get is 0 for this limit. It's very easy to concoct something like that. Let's think about the power series, sum of 2 to the n over n factorial. So here's the power series. We'll start it at 0 and run it out to infinity. And what I want is the IOC. Okay? And I claim that what you'll find if you do this, okay, what you'll find is that when you compute this limit here, you'll get 0. All right? Which will suggest, as per this stipulation, that if this limit over here is 0, then we interpret the radius of convergence to be infinity. Okay? So what I want you to check with your post-lecture slip today check that the radius of convergence is infinity, that r is equal to infinity. Okay? Now, what I want to say right now, with the remaining time that I have, is what it means for the radius to be infinity here. What it means is that no matter what value of x you put into this guy, so yeah, let's draw a picture. Here's the center. By the way, the center of this power series, a sub n is 2 to the n over n factorial, sorry, and the center is equal to 0. So we're going to have an interval of convergence which is centered at 0. But the fact that the radius of convergence is infinity means that sort of the width or the half width of this interval is infinite. Okay? So there are no endpoints, right? There are no endpoints to this interval. The interval of convergence is the entire real line. Which, if you like writing as an interval, you would write like this: negative infinity to infinity. Does that make sense? And so what does that mean? That means that no matter what value of x you choose, you can choose any value of x that you like. No matter what value of x you choose, this will be a convergent series. So, what am I saying? What I'm saying is, if you think of this as being like a function, okay? If you think of this as being like a function which eats values of x, what is the domain of that function? That is to say, what are the legit values that you are allowed to put into this function? All real numbers is the domain. All real numbers is the domain. You can stick anything you like into here and get a convergence series to get hence some value out. And here's a fact, which is very interesting. What value does this series here converge to? It converges to e to the 2x. E to the 2x power. That's what it converges to. Okay? And we will learn why that's so next week. But this concludes today's lecture. Okay? I know I went very fast. And this was probably a little bit confusing. I don't know. But I'll have a worksheet for you explaining all of this, reiterating all of these things that I said today on the internet this weekend. Okay? I also have to grade your midterms this weekend. So what a great weekend I'm going to have, right? All right. I love you all very much, and I will see you next time. Remember, we don't meet again until Tuesday. But I might release some quote-unquote bonus content or something like that, because I feel like I can really motivate well this fact and relate it to the ratio test stuff that we did, and I feel a little bit bad not doing that. So I at least want to do that once. I'll certainly, I'll certainly justify this in the worksheet. Okay, we'll certainly talk about this, why this fact is so in the worksheet. It comes from the ratio test, like I said. But for the purposes of what we're saying today, I think just knowing the bare fact is probably the most useful for solving problems right now. Like I said, I love you, and I will see you. Oh, and have a great weekend. I hope that the weather stays nice, or at least wherever you are. I hope the weather is nice. It's really beautiful out here in Davis. Okay, bye.